Hi guys. Uh, Today we will talk about, as you can see in the title, about determinants. But before we're gonna go and talk about this, let me make an announcement. I was asked by Liliana about the midterm exam. So the midterm exam, I think it was on, if I'm not mistaken, let me check. Let me double check everything so that. Um, So the midterm exam, we said that's going to be on next Thursday on July 1st and 2nd, right? That's what July 2nd. So midterm exam, midterm exam. So the midterm exam will be on July 2nd. That's going to be a 24 hours exam. And let me explain the procedure a bit. What are you going to do will be the following. I'm gonna post the exam will be posted on my website, and you will download whatever you want to do. You will write the solutions, and you're gonna send it to me and to my TAs. So send the exam. I will send you an email with precise instructions. The exam to the instructor and TAs. Make sure you do that. And you will send it as a single PDF file. I want to make myself very clear with this one. It's a single PDF file. Please don't send me thousands of pictures or whatever. Just send me a single PDF file. Okay. You'll have 24 hours, just like I said. There will be, I haven't decided yet, but given the fact that it's 30% of your grade, of your final grade, probably I will decide on maybe 5 or 6 problems, but probably I'll dwell more on 5 problems. Each problem is worth 6 points, 6%. There won't be any bonus questions since it's a 24 hours exam. What will include? So it will include,
I don't know.
3 chapters. The first 3 chapters. Or here and somebody's mic is on. I think Daniel or somebody's mic is okay. So the first 3 chapters, well, basically it will include systems of linear equations, matrices, and determinants. Okay. Determinants that we will study today. Also, I have decided, since the last time I didn't do too much about the I didn't talk too much about the elementary matrices. Today I'm going to do an extra lecture, just like last time. So probably in the evening, so extra lecture this evening, again at 8 p.m. So I'm inviting those of you who want to join. I encourage you to join also if you can. It's not mandatory. Even these lectures are not mandatory, only if you want to. And I could say one thing. Maybe I officially don't say it's I officially don't reward you with points but I will say it's gonna be good for you. All right. Yes, correct. Yes, Neil, it's correct. The first 3 homeworks are about the first 3 chapters. All right. So in this extra lecture that we will have this evening, we will talk about I will talk about uh, elementary matrices because elementary matrices and the LU factorization. I want to have this as a separate lecture since this is an important topic and I don't want to rush through things today. Okay, so this will be, and the material, like I said, it will be the first, absolutely, everything is uploaded on YouTube. Even the, I don't know if you have noticed that last week I have uploaded both lectures on YouTube. If you look, there is lecture number 3, which is matrices 1, and lecture number 4, which is matrices 2. And probably what I'm going to do today, so I will upload a video with this lecture about determinants, and then probably uh, I will upload another video with elementary matrices and LU factorization. All right. Do you have any questions regarding the midterm and everything like that? Anyway, I will send you an email so you'll have all the information in the email. By the way, I have a question for you. Do you actually look at my emails when I send them to you? Do you receive my emails? Okay, that's great. That's good. Okay, great. Good. Also, well, you know, I have a prejudice against Blackboard. I don't like it, but anyway, I also copied the same email into Blackboard in case some of you will be like, okay, I haven't checked my email, blah, blah, blah. Okay, but it's in your Blackboard. Yeah, I know. I hate Blackboard, but don't, okay, I said it now. It's going to be recorded. That's just my honest opinion. I really dislike Blackboard. No, I actually hate it. Hated it. It's the alternative. So you prefer email. But anyway, you know, I have to, as a requirement, because this is a distance course, I'm required by the university to put all the information that I'm on Blackboard first. So Blackboard is the primary interaction that we should have. All materials, videos, whatever should be posted on Blackboard in the first place. As I choose to do also by email and I use some other stuff, okay, that's up to me, but I must do it through Blackboard. Otherwise, trust me, I would have just ditched Blackboard immediately. But anyway, that's the rule. We have to obey by the rules. Okay. Do you have any other questions regarding the exam? No. Okay. So, like I said, the first 3 chapters all will include everything that I just said here. So basically, and also, you know, okay, I'm still debating, but
Yeah.
I was
Turn
thinking
off the AC.
I was thinking about
Window.
by the way, I think somebody has the mic on. Um, probably I'm going to do a review session for the midterm. I will record a review session, although I don't quite like to record things by myself. I will rather have some kind of interaction when I do a lecture. But anyway, I'll think about it. Probably I'm gonna do it just for you so that you can have some extra um, material for you to study for the midterm exam. Also, another thing I would suggest, and I think it's on my website, I would advise you to look at some of my previous exams. Uh, like I told you, I taught this class twice so far at Tech, and you will see, you can get a good idea of what to expect on the midterm exams. Okay. If there are no other questions, okay, let's start. So, like I said today, um, in any way, I will send you this lecture as a PDF as well, so it will be posted on my website, as you already know, used by now with this. Okay, so today we're going to talk about the determinants of a matrix. So, what is the determinant of a matrix? So the first question we want to answer: what is the determinant of a matrix? That's a very, very important question. But before we go and answer this question, I want to so keep in mind we have the matrix. Let's remind what the matrix is. So we have these entries A, I, J, with I is between 1 and M, and J is between 1 and N. And these will have the entries A11, A12, all the way to A1N, A21, A22, A2N, and we go all the way AM1, AM2, and AMN. So this is a matrix with M rows and N columns, right? M by N matrix. That's what we call it. And I think I mentioned something. I said that in the first lecture when we discussed the big picture of linear algebra. I mentioned something a bit about determinants. We can only compute the determinant of a matrix provided that the matrix is a square matrix. So in other words, we need M to be equal to N. That's the only way I can compute the matrix. So that we can compute the determinant of a matrix. We will see different techniques of computing the determinants, and you will see that this determinant, computing the determinant of a matrix, will be related to finding the inverse of a matrix. In other words, you will see another method of finding the inverse of a matrix using the determinant of a matrix. Okay, so but before we go into that, that's the condition you must have, M to be equal to N. So I need the matrix to be a square matrix. So if a matrix is a square matrix, then indeed I can compute the determinant of a matrix. And before I even go and do some examples of how to compute determinants of matrices, let me start with the case when M equals N equals 2. So in this case, we have 2 by 2 matrices. Okay, I'm going to put here square matrices, but this is redundant. So the matrix we're going to have is the following. A will have the entries A11, A12, A21, A22. So this is my matrix. And the definition, so the determinant of this matrix, let's call it like this, the determinant of A, or sometimes the notation is just A with, you're going to put it like this, something that you have seen before, the absolute value of, probably you've seen this in the college algebra, the absolute value of a real number, but you can put this, the absolute value of the matrix A. Anyway, so this will be the determinant, which will be this number. So we're going to multiply the elements on the main diagonal, and we will subtract the product of the elements from the secondary diagonal. So this will be nothing else than just A11 times A22 minus A21 times A12. So that's the definition. So it's very simple to compute the determinant of a 2 by 2 matrix. Very simple. This is the formula. And let me just give a very quick example. So a quick example is the following. So let's take this matrix A to B, and I'm going to take something like in the notes. Okay, let me take this matrix with the entries 2, 1, 4, 2. And probably is as by the definition above, the determinant will be 2 times 2 minus 4 times 1. So in this case, this is 0. The determinant of this matrix is 0. Okay. Let me give another example of another matrix. Let's say B. In my notes, I reversed this. So 2, -3, and 1 and 2. This implies that the determinant of B is 2 times 2 minus -3 times 1. So this is 4 plus 3, which is 7. And by the way, I want to make this remark that 7 is not 0. So as you can see, the determinant of A here is 0, right? But the determinant here is not 0. We will call these matrices, and I'll get back to it. The first matrix, it will be what we call a singular matrix. And you will see that these singular matrices do not have any inverse, unfortunately. Well, or fortunately maybe. And that the matrix B will be, since its determinant is not as a non-zero, this implies that the matrix is non-singular and therefore will be invertible. But anyway, we'll get back to that. But before we even uh, um, go and discuss about methods of computing inverses, I want to mention one thing which is very important, and I think this is very important for 2 by 2 matrices, and it's not mentioned in my notes, unfortunately, but anyway, I'll mention it here. So for 2 by 2 matrices, we'll have this kind of very nice equality identity, so which is called Cayley-Hamilton identity, and I want to discuss this. And I'm going to mention here for 2 by 2 matrices. So this identity that I'm going to give you, it's only for, in this form, will be valid only for 2 by 2 matrices. This says the following, and I will explain immediately if, in fact, I already mentioned that it holds for 2 by 2. So it says that, whoa, sorry. Okay, let me write it again. Cayley-Hamilton identity. And this says the following. It says that a squared minus the trace of a times a plus the determinant of a times the identity, right, equals the null matrix. Wow, what a beauty. Look at that. This looks amazing. Look at it. And let me explain what this means. And in this form is valid only for 2 by 2 matrices. So the trace of A, so if I have a matrix, let's say, so A is a matrix with the entries A11, A12, A21, A22. This means that the trace of A and by the definition, trace of A is nothing else than just by adding the elements on the main diagonal. So it's A11 plus A22. And the trace of A usually is valid in this, the definition of a trace of A is valid for n by n matrices as well. So you just add the elements on the main diagonal. The null matrix O2, let me remind you that this is 0, 0, 0, 0. All entries are 0. And the identity matrix, let me remind you that it's that matrix with ones on the main diagonal and the rest are 0. Okay, so this is the Cayley-Hamilton identity. It's a very nice identity, and probably I'll do more examples because um, I will do more examples when I will I'm thinking of having that recorded review session for the midterm exam. I wasn't planning for it, but probably I'll do it. I'll do more examples using this identity with problems that use this identity for in the review session. Okay. Okay, so this is the identity, and the way we prove this, let me mention one more thing. This is a very important identity because you will see at some point when we'll talk about in chapter number 6 about the eigenvalues and eigenvectors for 2 by 2 matrices and even for 3 by 3 and so on. You will see that this identity will have some implications regarding the eigenvalues of a matrix. But anyway, I'm not going to spoil it now. We will see it when we get there. Okay, so this is the identity. As you can see, there is a relationship between the square of a matrix, the trace of a matrix, and the determinant. That's amazing. Okay, the way we prove this, and frankly, I don't want to, let me just give the main idea. So the idea of the proof of Cayley-Hamilton. Basically, you just do computations. You write A to be A11, A12, A21, A22. And you look, who is trace of A? So I know trace of A is A11 plus A22. Okay, that's a scalar. All right, let's compute A squared. Who is A squared? So A squared by the definition is A times A. So in other words, this is A11, A12, A21, A22 times the same thing. And now you just multiply these. Oh my. Now so the first one will be A11 squared, right? Plus, let me write it here because it's going to be a long, big matrix. So this will be equal to, do it like this, A11 squared plus A12 times A21, right? Now we're going to take the first row and multiply with the second column, A11 times A12 plus A12 times A22. Now, here A21 times A11 plus A22 times A21. And here, the last one will be A21 times A12 plus A22 squared. Okay. So that's the A squared. And now you look at which one is trace of A, which is a scalar, by the way, times A. So this is A11 plus A22 times this matrix, A11, A12, A21, A22, right? And we multiply, we know how to multiply matrices by scalars. So basically you just multiply the scalar by each entry of the matrix. So this will give us, let me put it here, A11, okay, let me write like this, A11 squared, right? Plus A11 times A22. Then we will have A11 times A12 plus A22 times A12. Then we have A11 times A21 plus A22 times A21. Okay, and now the last entry will be A11 times A22 plus A22 squared. Okay, so that's trace of A times A. And now the only thing that's left for you is to compute the determinant of A times the identity. So this is the determinant, as you remember by the definition, is what? Is A11 times, let me see, A11 times A22 minus A12 times A21. And when you multiply this, again, this is a scalar. When you multiply this, it's going to be this matrix, A11 times A22 minus A12 times A21, 0, 0, and the same thing, A11 times A22 minus A12 times A21. Okay, and after you put everything together, all this mess, and I'll leave it to you as an exercise, that A squared, when you compute this, minus trace of A times A plus the determinant of A times the identity will give you indeed the null matrix, will give you 0. I will leave it to you as an exercise to check that this is indeed 0. I don't think I made any mistakes in computation, so you can see it for yourself. Okay, so I'll leave it to you as an exercise here. So we have all, we have this, we have this, we have this. So you just have to add, subtract, and then you'll get the result. All right. So this is what happens for 2 by 2 matrices. Keep in mind this identity. Once again, I haven't, unfortunately, the book does it. My notes, I don't deviate in my notes. I don't deviate too much from the book. So because the book, it's that's the requirement for this class. So I I didn't deviate too much, but when I felt the need that I should provide some extra explanations or to explain some things better, or I don't know, to show you something that I find relevant, I did not hesitate to do so. And this is one of them. There will be some other things as well. So this is one of them. That's why I also send you this notes, and I want you to look also these notes as well that we're gonna take in class, not just the notes that I send you before the class, so that you can read them before the class starts. All right, so this is one of them. Look at it. This is a beauty, absolute beauty when you look at this identity. Oh my goodness. Um, um, we'll see more applications. You'll see how this can be used to prove many things. But anyway, okay. So now I want to talk about. So let me go back to the. So what is the determinant of a matrix? Well, now we have answered this, but only for this case, for m m equals n equals 2. So we answered this for square matrices of size 2. Okay. Now let's veer towards how to compute matrices, determinants, sorry, for matrices of size at least 3, right? Anyway, but before we go into that, let me talk about minors and cofactors. Well, why are these important? So minors and cofactors are important in order to define or to compute, basically. Or maybe I should say compute to be consistent. Determinants of matrices um, of order higher than 2. So just like I said, for example, for 3 by 3 matrices, you will see that for 3 by 3 matrices, the way we're going to compute the determinant will not be the same as we computed for a 2 by 2 matrix. This is very important for you to know. So it's not going to be like I'm going to multiply the elements on the main diagonal and I'm going to subtract the product of the elements of the secondary diagonal, whatever that is. You'll see that the situation will be a little bit more complicated, but also I'll give you this rule, which is I would say something very slick for you to compute determinants of matrices of size 3, only for 3 by 3. But anyway, we'll get there. Before we go into this, let me just define. So let's define, so definition. So we want to define the minors and the cofactors of a square matrix. So if A is a square matrix, and this is very important, I'm gonna keep mentioning this, it's a square matrix, then the minor let's call this Mij, right, of the entry Iaj is the determinant, obtained by deleting the ith row and the jth column of A. And now the cofactor Cij of the entry Iaj is given by, and I'm going to write this formula here, Cij is nothing else than just -1 to the power A plus j. So we add the entries times, guess what, the minor, Mij. So that's the cofactor. This will be very important, the cofactor of a matrix. We will use this when we'll compute the inverse. Anyway. So for example, let me give an example, of course. Well, I can give the example of a 2 by 2 matrix, but that's going to be very easy to see. So this applies. So one remark here, very quick. This applies when I say square matrices, I mean including 2. So you can apply this thing with the cofactor and with the minors also for 2 by 2 matrices. But make sure this is a square matrix. This is very, very important here. Very important condition. Okay, now let me give you an example. And the example that I have in mind, and I want to use the example from the notes, is if A is a 3 by 3 matrix. So let's write it. So this would be A11. So we'll have these entries. Okay. And what I want to do is I want to compute some minors and cofactors. So the questions that I want to address is that what are the minors and cofactors of, let's say, what elements? Let's say A21 and A22. So of these two entries. So in other words, let me identify them here. So A21 is right here. A22 is right next to it. So they're right next to each other. So let's compute using our definition the minor of the entry A21. So in other words, I want to compute M21. So by the definition, if we look, we said that is the determinant obtained by deleting the second row in our case and the first column. So this is the determinant obtained by deleting the second row and first column. Okay, now my question to you, since it's the determinant of this, what kind of, it will be the determinant of what kind of matrix? What is the size of that matrix? Can you tell me? It's a 2 by 2. Exactly. So it's going to be a 2 by 2. So M21 will be the determinant of, so I'm deleting this row here, right? And this column here. So it will be what? A12, right? A13, and then A32, A33. And guess what? I know how to compute the determinant of this, right? So this would be A12 times A33 minus A13 times A32. So I know how to compute this determinant, which is great. But also I can compute the cofactor C21 of this minor. So the cofactor will be -1 to the power 2 plus 1 times M21. And this is nothing else than -1. This will be -1 times this guy here, A12 times A33 minus A13 times A32. Okay. And we can keep going. We can compute this. So in other words, this is nothing else than just -M21. So that's the point. So as you can see, the cofactor, they don't deviate too much from the minor. So it's just going to be, it will be a negative or it will be positive. Basically the same thing as the minor. For example, the minor of 2, right? So in the same fashion, we can say that the minor M22 is just the determinant obtained by deleting the second row and the second column. So this will be what? It will be again a 2 by 2, the determinant of a 2 by 2 matrix, and this time we'll have A11, A13, and A31, A33. Right? And we can compute this. This is A11 times A33 minus A13 times A31. Okay, so that's the determinant. And now, surprise, the cofactor, C22, is nothing else than just -1 to the power 2 plus 2 times M22. So this is, it's the same as the minor, M22. And you can keep going. So let me point out the remark here. The minors and cofactors of a matrix, can differ only, in sign. That's it, just like I said. Probably you have on odd position we'll have negative signs. On even position we'll have positive signs. And well, there is an example in my notes, example 2, which says the following: find, and perhaps that's a good idea of finding this, find all minors and cofactors of the following matrix. Oh my, let's do it at 3 by 3. That's going to be painful. 0, 2, 1, 3, negative 1, 2, 4, 0, 1. Okay, so this is a 3 by 3 matrix. So that, and guess what? How many minors do we have to compute? Can you tell me? 7? Really? 9? Well, anybody? 9? So yes, that's correct. 9. We have to compute 9 of them. Look, only for this, only if you look at the first row, we have to compute 3 minors. In the second row, another 3 minors, and then on the third row, another 3 minors. You see, somebody asked a question here, Morgan. Morgan asked the following question: do the zeros count? That's a very good question. You have something in mind with the zeros, but that will count. Yes, they will count, but with the zeros will be very important when we will compute the determinant of a matrix, because I will expand on a row or a column where there are more zeros, so that I can get rid of computations. But anyway, we'll get to that. The zeros will count when we will compute. We'll count in the following way. When we will want to do very convenient computations of the determinant of a matrix. Anyway, we'll get there, and I think the picture will be clearer for you. Okay, so now let's compute the minors. Oh my God. Oh my. So let's see, M11. Okay, I'm just gonna compute a couple of them, and then, so M11 will be, so keep in mind, I'm gonna delete the row, the first row and the first column, right? So it will remain only this matrix here, as you can see, only this guy here, right? So it will be the determinant of, of this matrix, -1, 2, 0, 1. And the determinant of this is -1 times 1 minus 0 times 2, which is -1. Okay. Again, I'm going to do the same thing for the M12. It will be what? Well, you look at this guy, you take and it will delete the column and the row. So it will be the determinant of 3, 2, 4, 1. So this will be 3 times 1 minus 4, 2 times 4, which is -5. And you keep going. Let's do one more. M13. So again, you delete the first row and the third column. So it will be the determinant of 3, -1, 4, and 0. So this will be 3 times 0 minus -1 times 4, which will be 4. Okay, in the same way, one can compute the rest of minors. So these minors, so let me just mention the rest. So M21, I'm just gonna, is 2, M31 is, M22 is -4, M23 is -8. I hope I didn't do any mistake. Anyway, you'll check it. M31 will be 5, M32 will be -3, and M33 will be -6. Well, I hope these are correct. Anyway, you can check them. So you see, there are 9 minors in total. 9 minors in total. Wow, 9 of them. Okay. In the same fashion, you can find the cofactors. So the cofactors can be computed in the same way. So C11 will be -1 to the power 1 plus 1 times M11. And this will be exactly as M11, which we computed previously, and so on. I think you can do it by yourself at this point. Okay, now the question is, why are these important? So I want to go back to this, the first question. Well, I said that these are important to compute the determinant of a matrix. So the question is, how to compute the determinant of a matrix using minors and cofactors. Okay. So we want to use these two notions to compute the determinant. So let me give you the following definition. So the definition of a determinant of a matrix. And by the way, this will be valid for all square matrices. So if A, I'm going to mention again, is a square matrix, of size n, and this n is greater or equal than 2. So as you can see, I include also the 2 by 2 matrices. Then the determinant of A, right, is the sum of the entries in the first row. And now, okay, I'm gonna point out something of A multiplied by their respective cofactors, multiplied by their respective cofactors. Well, here, in fact, this is given by the following formula. Let me just write the formula and then I'll explain it. So the formula is the following. The determinant of A, or sometimes if you want to denote it like this, A in absolute value, it will be the sum from j equals 1 to n. And now we said that is the sum of the entries in the first row. That's something that I don't like, but anyway, let's write it like this. So it's A1j, because we said the first row, times C1j. So this will be nothing else than just, let me write it. So this is A11 times C11 plus A12 times C12 plus all the way to A1n times C1n, where these C1, where Cij are the cofactors. Anyway, that's the formula you need to know for computing the determinant of a matrix. And now I want to point out a remark, because I don't quite like this definition. Well, it might be misleading. And you see, let's look at it. Let's look at it again. So it says that this is the determinant is the sum of the entries in the first row of A multiplied. Not, I want to say something. I want to make myself very clear here. It's not necessarily only the first row. So you can put there the second row, the first column, whatever. So this definition is called the expansion on the first row of A. So you can expand on any row and any column you want. So, but so please don't stick to the first row. So the most important thing for you is to expand over a row or a column where you will see many zeros, just like somebody said here. You see Morgan's said something about those zeros. So let's see an example so that you can see it. So we see an example, quick example on how to use this definition. Okay, let's find the determinant. So find the determinant of the following matrix. Let's say 0, 2, 1, 3, negative 1, 2, 4, 0, 1. Okay. So if I'm using the exact definition, so I have to be focused on this row here, right? But like I said, it doesn't matter on which one you're focused. So the determinant of A, so we need to compute the so the determinant of A, by the definition, determinant of A is nothing else than just the position A11 times C11 plus A12 times C12 plus A13 times C13. But in the same way, in fact, let's compute this, and then you'll see that if I expand, so I'm expanding on the first row. So this is expanding on the first row. This is how we call it. So this is row 1 here, right? Okay, so let's use this definition. As you can see, I need to compute the cofactors. So let's do it. So let's see, C11 is what? Is negative 1 to the power 1 plus 1 times M11. C12 is negative 1 to the power 1 plus 2 times M12. And finally, C13 is negative 1 to the power 1 plus 3 times M13. Okay, I will leave it to you and you'll tell me what this is. So these will be some numbers. So I want you to tell me what C11, C12, and C13 are. Musfik says -1, and Lydiana. So it's so it's -1, 5, and 4. Yeah, I got the same thing in my notes. Okay, so now it's easy to compute the determinant. So this implies that the determinant of A or if you want, you can use this notation, will be what? Will be A11, which is what? It's 0 times -1 plus A12, which is 2 times 5 plus A13, which is 1 times 4. And this will give us what? 14, right? Okay. Now, I want you to do the following exercise. What if I expand over the second row? I want you to. So the question is, and I'm going to write it, what happens if we expand over the second row? I want you to tell me. So in other words, I'm having the following formula. So A21 times, A21 times C21 plus A22 times C22 plus A23 times C23. I want you to tell me what this is equal to. Well, I want you to tell me. Just compute it. So you know who these A1, Aij are. So the only thing you need to compute are these guys right here. And I want you to tell me what you'll get. Just let me give you 2 minutes. Think about it. So do we get, the question is, do we get the same thing? Well, the answer is yes. We do get the same thing. So this will be 14. You see, this is why I have a little bit of a problem with the definition, because let's look again at the definition. It says of the entries in the first row. No. I will, well, I wrote this definition on purpose because I want to confuse you a bit on purpose. But you can change it with the following. You can say is the determinant of a matrix is the sum of the entries on the row that I want, or the row that I like, not necessarily the first row. Row or column, pay attention. In fact, I want you to do this exercise. I want you to expand over a column. For example, I want you to do this thing here. So for example, if you compute, let's say, A11 times C11 plus A21 times C21 plus A31 times C31. Guess what? You will get the same thing. So, yep. So this is how you compute the determinant of a matrix. And since I don't want to, yes, you can, I'm pointing already these remarks. So in other words, let me write the exact, the expansion by the code, the exact theorem, so that I make myself even clearer. So theorem, expansion by cofactors. So let A be a square matrix of order size, it doesn't matter. The book uses order. Sometimes I use size of order n, but it's the same thing. So I hope this is not confusing to you. Then the determinant of A, just like I said, is given by is, and I'm going to write with green. So this will be determinant of A, or you can write it like this. This will be the sum from j equals 1 to n. And now I'm not going to write this on the a1j. I'm going to write this aij times cij. You see, I'm replacing one by, which is ai1 c I1 plus AI2 times CI2 plus da-da-da, all the way to IN times C IN. So this is what we call the ith row expansion. But you can also expand in the same way. You can also expand on the column as well, just like I said. So, or for example, or you can write this as in the same way. This will be, let's say, the sum from this time from I equals 1 to n of aij times cij. And now I'm expanding on the jth column. So this will be aij times, oh, sorry, a1j a1j times c1j, right? Plus a2j times c2j, plus all the way to a nj times c nj. And this is what we'll call the jth column expansion. So it doesn't matter. You can expand on rows, you can expand on columns, it doesn't really matter. This will get the same thing. So the determinant will stay the same. Okay, so these are the two formulas. Look at them. The two formulas. It doesn't matter. You can, like I said, you can expand on anything you want, row, column, but I think the most convenient expansion for you will be to have something like um, a row or a column with as many zeros as possible. For example, let me point out this example from example 4 from the notes. Ooh, time flies by. So find the determinant of the following matrix. A is, and I'm going to give you a 4 by 4. Well, 1, -2, 3, 0, -1, 1, 0, 2, 0, 2, 0, 3, 3, 4, 0, -2. Okay, I want you to tell me. So I want to find the determinant of A. What do you think will be the most convenient for you? What is the row or the column that looks the most convenient for you to expand upon? The third column, you see it? Let's look at it here. Look, the third column. Because we have as many zeros as possible. So if I expand on the third column, so this would be what? Keep in mind that this is, so it will be what? 3 times C13 plus 0 times the what cofactor I have here, C23 plus 0 times C33 plus 0 times C43. Well, that's amazing because all these guys vanish. This guy is 0, This guy is 0. I don't even need to compute them. This guy is 0. So the only thing I'm left with is 3 times C13. And this is C13, right, is this element here. So I'm deleting the row, the first row and the third column. So this will be -1 to the power 1 plus 3 times the minor M13, which is nothing else than just -1 to the power 1 plus 3 times. And the minor, guess what, will be what kind of determinant of order what? So what kind of matrix do we, 3 by 3, correct. So I have a 3 by 3 matrix. So this will be -1, 1, 2, 0, 2, 3, and 3, 4, and -2. And well, you can compute this. Again, you can expand. All the computations are done in the notes, and I'll leave it to you as an exercise, so details. But you can also find them in the notes. After you do this, then this implies that the determinant is 3 times 13, which is 39. That's how you compute the determinant of a matrix. Okay, let me give you a slick rule. I said it. Let me point out a remark, because this is very important. Oh, so there is an alternative way of computing the determinants of matrices of order 3. But this trick works only for matrices of order 3. That's it. Doesn't work for matrices of any other order. That's it. Keep that in mind. And what is called the Cezar's rule. So when I remember, this is not given in the book. I put it in my notes though, but I was surprised to see that it's not done in the book. This is a tricky way of learning how to compute the determinants of 3 by 3 matrices. I remember I was very excited about this when I first learned it. Anyway, we do linear algebra in high school in Romania. And I was like, wow, this is a nice way of doing this. And it says the following. So I'm going to write it in the following way. So pay attention. So I have this matrix. Let's write it. A11, A12, A13, A21, A22, A23. And now the last row is A31, A32, A33. Okay, so this is the matrix. And I'm going to mention here is a 3 by 3 matrix. That's it. It doesn't work for any, this trick doesn't work for 4 by 4. So I want to make myself very clear. What I'm going to do, since I want to mimic something similar with the 2 by 2 matrix, I'm going to do the following. So I'm going to write the first 2 rows. So this will be A11, A12, A13, A21, A22, A23. So I'm rewriting the first 2 rows, and then guess what? I'm going to do it like this on the diagonal. I'm going to multiply these plus the multiplication of this plus the multiplication of this minus, let me point a different color. Okay, minus the minus the multiplication of this times the multiplication of this times the multiplication of this. So this is what we call the Cezar's rule. So let's write this. So the determinant of A, so this is, let's say, the determinant of A. The determinant of A, this will be equal to the following. And I'm going to write it like this. A11 times A22 times A33 plus A21 times A32 times A13 plus A31 times A12 plus A23, and now minus, and I'm going to multiply the elements on the these diagonals, so it will be A13 times A22 times A31 plus A23 times A32 times A11 plus the last one is A33 times A12 times A21, and that's it. So if you want to go back, you can take the same example. So if you want to play, so this is the same thing. So there's also example number, examples. I want you to check example 7 from page, well, 12. Well, page 12. It depends on how you look at it. In the notes, is numbering is 89, but in the files is 12. So that's what I mean. Anyway, you'll find it. It's how to use Sarus rule to compute the determinant of a 3x3 matrix. And I want to stress that again. It's only for 3x3. This trick works only for 3x3. Well, the diagonal rule for all square matrices. So you want to work, okay, I want to understand. So your question basically, is there a trick with using this diagonal rule for other square matrices as well, for 4x4, for 5x5, and so on? So that's what you're asking? Unfortunately, none that I'm aware of. I mean, there's also triangle rule, which is similar to Sarus rule, but nah, that's something tricky like this, no. Unfortunately, for 4x4, the most convenient thing for you to do is to do expansion. That's what I would suggest. Okay, so now I want to talk about the bit of triangular matrices, and probably, oh, it's already, dang. And probably in the other lecture, probably I'm going to do it again, just like I did it last week at 8 p.m. So I invite you, more than welcome to attend if you want to. It's not, I won't give you any extra points, but let me put it this way. I will look to see who is there, who is really interested. You never know. The only thing I could say is that it will not play against you in any way. That I can guarantee it. And usually in the evening, well, last time we had, there were only, I think, 8 p.m., but I will send you an email though. Don't worry, just like last time. We only were like 4 people, and the people felt more relaxed asking questions, you know, like speaking, which is which I encourage you to do also. If you can also be vocal with your questions. I wouldn't mind that. We can also write on the chat, but for me, if you see, I have to be to pay attention in 3 places. I have to pay attention to what is written here. I have to pay attention to there. Then I have to pay attention also to the chat to see who's writing. Then I have to pay attention to see what things I'm covering from the notes and so on, examples and so on. So I'm looking at 4 things at the same time. So I have to be like this. So I would also encourage you to speak, which is because the questions, I might not see them immediately. So I have to see, well, let's see. I'm notified there, there's a question. So basically I'm interrupting myself most of the time. Anyway, so I want to say this again. This Sarus rule works only for 3x3 matrices. And now there is one thing that I want to mention. And before we, maybe at 8 p.m., I will discuss more about the properties of the determinants, and also I'm going to talk about the LU factorization. Usually in the book, the LU factorization is given before the determinants, but I'll show you something tricky, which will allow you how to compute the LU factorization of a matrix using the determinants, or under what conditions we can compute the LU factorization of a matrix. Anyway, I'm not going into that now. So now I want to talk about what about the determinants of triangular matrices? What if, but before we go into that, what is a triangular matrix? Because LU factorization that we will talk about in the evening will have something to do with the triangular matrix. So a triangular matrix, well, let's write in words. So it can be upper triangular and lower triangular. So it says it's upper triangular when it has all zeros entries, when it has all zero entries below its main diagonal. Ouch. Entries below its main diagonal. Below its main diagonal. And of course, as you can expect, a lower triangular is when it has, oh my goodness, what am I writing here? When it has all zero entries above its main diagonal. Okay. And of course, when a matrix is both upper and lower triangular, in other words, it's just diagonal. So when a matrix is both upper and lower triangular, then we say that the matrix is, then we say that we call it, when it's both upper, then we call it diagonal. So in other words, a diagonal matrix is something that has only entries on the diagonal and the rest are zero. That's it. For example, let me give you a quick example of a matrix. Let me consider this matrix. Let's take a 3 by 3, and this will be 2, 3, -1, 0, -1, 2, and 0, 0, 3. So this is the main diagonal, as you can see it here, right? And now, what can you tell me? You see, below the main diagonal, all the entries are zeros, right? Look at them. So what can you tell me about this matrix? How is it? Is it upper, lower triangular? It's upper triangular. And I will leave it to you as an exercise to compute the determinant of this. Upper triangular. I will leave it to you as an exercise to compute the determinant. I'm just going to give you exercise for you to do it. Well, as you can see, you can. What will be the most convenient thing for you to do when you will want to compute the determinant? Is to expand on the first column, right? But anyway, you can do this, and according to my notes, the determinant is actually -6. But there's a general theorem which says the following, and with this, I'm gonna. How to compute the determinant of a triangular matrix? It says the following: if A is a triangular matrix of order n, then its determinant is the product of its entries on the main diagonal. In other words, we'll have the following. The determinant of A is nothing else than just A11 times A22 times AN. So there you go. You have a formula. You know that the trace, we've said that the trace of a matrix is the sum of the elements on the main diagonal. In the case when the matrix is a triangular matrix, the determinant will be the product of the elements on the main diagonal. And with this, I will stop here. So let me see how many people, 65. I'm gonna take the attendance. Let me stop the video. Okay, there's a question though. On page 6 or 83, how do we know the numbers change their sign? 83. Page 6, okay. For example, M21 and M, because, yes, because C21 is nothing else than -1 to the power 2 plus 1, which is -1 to the power 3, which is -1. So it will be negative M21. Do you understand now? So C21 will have the same sign as C12. And I think I mentioned in the notes, I think. Yeah, the odd ones will have, it's clear, right, Eduardo? Okay. All right. So let me stop the recording.